Hey guys, and welcome to lesson 10b, exponential functions. We're going to start off just by exploring two different exponential functions. The first is f of x equals 2 to the x, and then g of x equals 3 to the x. So usually whenever we're exploring a function for the first time, we plug in some points to help us just see what's going on. And we usually like plugging in -2, -1, 0, 1, 2, and I'm going to add 3 onto our list here. We're going to do the same thing here. -2, -1, 0, 1, 2, and 3. All right, so if I have 2 to the -2, well, that's the same thing as 1 over 2 squared, which is 1/4. So my y value here is 1/4. So similarly, if we do 2 to the -1, that's the same thing as 1 over 2, so that's 1/2. Anything to the 0 is 1. 2 to the 1 is 2. 2 squared is 4. 2 cubed is 8. So let's graph it and see what that looks like as a function. So I've got -2 1/4, so that's close to the axis. -1/2, which is here. 0, 1. Then 1, 2. 2, 4, and then 3, 8, which is right here. So you guys can see that this makes this really nice curve here where we're going like that. Well, now let's compare that if we change our base from 2 to 3. Well, 3 to the -2, 3 to the -2 is going to be equal to 1 over 3 squared, which is 1/9. Okay, so that's 1/9. 3 to the -1 is just going to be 1/3 because all we do is we flip it. 3, anything to the 0 is 1. 3 to the first is 3. 3 squared is 9. So let's graph that now. So we've got 1/9, -2, 1/9, which is right next to but not quite on the axis. -1, 1/3, which is going to drop down below this. 0, 1, same point as before. 1, 3. Oh, and then, by the way, 3 cubed is 27. And then 2, 9, and then 3, 27 would be way the heck up here. So when this graphs like this. So what was the difference between these two? Looking at this, when I change the base to a larger number, the actual, it decreases closer to 0 faster, and it increases on the other side quicker as well. So it approaches infinity faster and it approaches 0 faster. So that's really the big idea. Now let's take a look and see what happens if we make our bases fractions. Well, if I have 1/2 to the x, we're going to plug in our same test points. -2, -1, 0, 1, 2, and I don't see the need for 3, and you'll see why here in a second. But we might take a look at -3, okay? And then -2, -1, 0, 1, 2. Well, if I take 1/2 and I raise it to the -2, well, that's the same thing as flipping it and doing 2 squared, which is 4. So that guy's 4. Similarly, if I have 1/2 to the -1, we flip it because it's got a negative exponent, we just get 2. Anything to the 0 is 1. Anything to the 1 is itself. And then 1/2 squared is going to get me 1/4. And then if I have 1/2 to the -3, that's the same thing as 2 to the 3rd, which is just 8. 8. Come on, 8. There we go. So let's graph those. So I've got -3, 8, 3, 4, 5, 6, 7, 8. -2, 4. -1, -1, 2. 0, 1. 1, 1/2. 2, 1/4, which is here. And so on and so forth. So we get a really similar curve to the thing we got before, right? But we're noticing that it's just going the other direction. Really similar curve. So now let's take a look at what happens when we change our base to 1/3. Well, 1/3 to the -2 is going to produce, that's the same thing as 3 to the 2, which is 9. 1/3 to the -1 is 3. 1/3 to the 1 is 1/3. 1/3 square is 1/9. So let's graph that. So we've got -2, 9, -1, 3, 0, 1, 1, 1/3, just landing just down here, 2, 1/9, so on and so forth. So again, we're getting a very similar curve to what we got before. It also is steeper, right, than the previous one and approaches 0 faster. So we've got some themes here. So let's make some summaries then of what these look like. If you notice, both of these also will never cross the x-axis. We've got this line right here, the x-axis. Both of these will always approach it but never actually cross, because as long as my b value is positive, then we can never actually produce a y value that's negative. We call this line an asymptote. And an asymptote is a line in which the graph gets very, very close to but never actually crosses. So when we just have the basic function f of x equals b to the x, where my b value is positive and b does not equal 1, because 1 to anything is 1, right? Then my asymptote is going to be the x-axis, or if we're going to write that as an equation, the line y equals 0. My y-intercept similarly is always 0, 1. Right? There is no x-intercept because we never cross the x-intercept. And my domain, I can plug in any value of x I want. So we could say my domain is all real numbers, or -infinity is less than x is less than infinity. That's the same way to write that. Whereas my range, my y value has to always be greater than 0. And again, both of these concepts come back to the idea that you have an asymptote, right? We can plug in any value for x, but my y value can never actually be negative. We can never be 0. We can get right up next to 0. Y could be 0.00001, but it can't be 0. That's what it means to have an asymptote. So all exponential graphs of the form y equals b to the x actually have two pretty points. Our first one is always going to be at 0, 1, because anything to the 0, any number I put in for b, if I raise it to the 0, the y value is going to be 1. And my second point is always going to be at 1, b, because any number raised to the first power just produces itself. So let's take a look at how we actually solve exponential equations. So looking at this, the big idea here is to express each side as a power of the same base. So here, if I have 2 to the x equals 16, my first step is to re-express both sides as bases of 2. 16 is the same thing as 2 to the 4th. Because if I end up with two exponential equations with the same base, then that means their exponents must be the same. So this just gets me that x must be 4, because if 2 to the x equals 2 to the 4th, then x must be 4. Similarly here, I'm going to rewrite both of these as base of 2. So 4 is 2 squared, and then we still have that x plus 3 hanging out there, whereas 8 is 2 cubed with an x still hanging on. So that means that 2 times x plus 3 must be equal to 3x for these equations to work. So I get 2x equals 6, or 2x plus 6 is equal to 3x. Well, that means that 6 must be the value of x. And what I want to do is I want to go back and plug in to make sure this works. So does 4 to the 6 plus 3 equal 8 to the 6th? Well, I'm going to check. Does 4 to the 9th equal 8 to the 6th? That's why we've got a calculator. I am going to do 4 to the 9th, and I'm going to do 8 to the 6th. And look, I get the same answer, so it works, right? But let's keep going. Down here, we've got two equations, 9 to the 2x minus 1, and then x I have 9 to the 2x minus 1 and 27 to the 4x plus 2. So to set this up, I'm going to go through and set both of these to common bases, which in this case is going to be 3. 9 is 3 squared, and then we still have that exponent of 2x minus 1. Whereas 27 is 3 cubed, and we still have 4x plus 2. So now that we've got them in the same bases, I can just set my exponents equal to each other. Sorry, that should be 2x minus 1. So now I have 2 times 2x minus 1. That should equal 3 times 4x plus 2. So I go through and I solve this. I get 4x minus 2. I want to know, does that equal 12x plus 6? So we solve it. I subtract the 4 over to get 8x. I subtract the 6 over to get negative 8. So I get negative 1 equals x. Now I'm going to test and make sure my answer actually works. Okay, so I'm just going to do this. I'm going to do 9 to the 2 times negative 1 minus 1. And I want to know, does that equal 27 to the 4 times negative 1 plus 2? That should be a plus, not a 4, I promise. Plus 2. So I get, does 9 to the negative 3 equal 27 to the negative 2? Well, let's test it. 9 to the negative 3, does that equal 27 to the negative 2? Yes, it does. So we're good to go. Those work. All right, guys, let's now take a look at D. Sorry, I'm going to erase my check. Okay, so in D, I have 4 to the 2x equals 1/2 to the 1 minus 2x. So my first step is to write both of these in common bases. A good common base here is 2, because 4 is 2 squared. We still have to the 2x. Whereas 1/2 is 2 to the negative 1, and we still have the exponent 1 minus 2x. So I go through, I'm going to set my exponents equal to each other. 2 times 2x equals negative 1 times 1 minus 2x. Or does 4x equal negative 1 plus 2x? So I get 2x equals negative 1, or x equals negative 1/2. We're going to check, right? I want to know, does 4 to the 2 times negative 1/2, does that equal 1/2 to the 1 minus 2 times negative 1/2? Okay. Well, 4 to 2 times negative 1/2 becomes, does 4 to the negative 1 equal 1/2 to the 1 minus negative 1? Or does 1/4 equal 1/2 squared? Indeed it does, so that works. Checked my answer. All right, guys, you guys have trime's now. Go ahead and see if you can figure them out. All right, guys, take a look and see if your answers match, and let's go on to our last section. All right, the exponential function defined by a equals p to the 1 plus r over n to the nt models the dollars accrued or owed after p dollars are invested or loaned at the annual interest rate. Guys, if you learn one thing in any high school math class, this is it. Because, guys, this is how interest is calculated. So anytime you buy a car, anytime you do a mortgage on a house, anytime you have anything that carries interest, this is how your interest is being calculated. So learn this. This is very important. And basically, what this formula does is it calculates, if you're buying something on interest, how much money are you actually going to pay for something at the end of the day? And so the big idea is to go through and identify your variables. So P is your initial dollars invested, okay? R is your interest rate. N is how many times you compound it, and T is the number of years. So let's take a look and define our variables for this problem, and then we're going to finish it in class. The amount owed at the end of 5 years if $1,600 is loaned at a rate of 9% compounded monthly. Well, we start off with $1,600, so that's my principal. My rate is 9%, but remember we have to write it as a decimal, so my rate is 0.09. If we compound monthly, that means we're compounding 12 times in a year, go for a total of 5 years, and I am hunting